let's calculate the limit from 0 to square root of n as n approaches infinity of integral 0 to square root of n of 1 minus x squared over n quantity to the power of n dx. So I want to get rid of n down here. So to do that, I can let x equal to square root of n times t. Notice the boundaries are positive, 0 to positive, so x must be positive. Right, so that means t must be positive. So that way dx is equal to square root of n dt. Right, so when x is equal to 0, right, t is equal to 0. When x is equal to square root of n, then t is equal to 1. Right, so new boundaries. Right, the integral new boundaries from 0 to 1. Right, that way I have quantity 1 minus. Right, this time x squared is equal to n times t squared. Right, so x squared over n t squared over t squared. Quantity to the power of n dx. dx is equal to square root of n dt at this time. So again, I can let t equal to sine theta. Right, so that way dt is equal to cosine theta d theta. So that way in is equal to this time our new boundaries. When t is equal to 0, theta is equal to 0. When t is equal to 1, theta is equal to half pi. Right. So this time I should have 1 minus sine square theta, quantity to the power of n times square root of n times dt becomes cosine theta d theta. So take out the square root of n, then times integral from 0 to half pi of cosine to the power of 2n, and then cosine. So cosine, this time the power should be 2n plus 1 of theta, d theta. Right. Then we calculate the limit. So perhaps I use Wallis formula, right? Wallis integral. So this integral is equal to, again, the power is 2n plus 1. So 2n plus 1, quantity double factorial, then 2n double factorial. An odd power, so there's no half pi here. So we're essentially calculating this limit. So again, I'm using Wallis formula. So according to Wallis, the limit of 2n double factorial quantity squared over 2n minus 1 double factorial times 2n plus 1 double factorial approaches half pi as n approaches infinity. Right, so in other words, if I multiply by 2n plus 1, both top and bottom. Right, 2n plus 1 multiplied to this factorial, so this 2n minus 1 factorial now becomes 2n plus 1 factorial, right? And I have twice of them. So 2n plus 1 factorial, double factorial, quantity squared, this time, approaches half pi. Right? So I'm looking to, because I want to substitute this with something else. Right? If I take the square root on both sides, I should have 2n factorial times square root of 2n plus 1 over 2n plus 1 double factorial approaches square root of half pi as n approaches infinity, right, this time. So which means 2n double factorial over 2n plus 1 factorial, right, is, so this divided over to there, right, this, so approaches 1. So meaning this over that, it's a reciprocal. Right, so this over that, reciprocal is what? The square root of pi over 2 over square root of 2n plus 1. That's its reciprocal. So in other words, this and that are asymptotically equivalent. So in other words, they approach infinity at the same speed, right, as n approaches infinity. So meaning I can replace this with this quantity when it comes to limit. So all I need to do is to calculate, is to have a look at the limit of so square root of n times square root of 2n plus 1, right, at the bottom, and square root of pi over 2. Does this have a limit? I think so, right? So I can divide both top and bottom by square root of n, right? I have square root of pi over 2 over, under the square root, I should have 2n over n plus 1 over n. That's the result. I divide by square root of n, right? So under the square root, I have everything divided by n. So in this case, and this simply approaches 0. All right, so the whole thing will approach square root of 2 at the bottom, square root of pi over 2. Right, so meaning square root of pi over 2. Like I said, square root of 2 at the bottom. Right, so square 2 at the bottom this time. Square root of pi as n approaches infinity.